is post-training small language models, the adventures of a practitioner. I am the practitioner. I'm Stefano Fiorucci, an AI and software engineer. I'm passionate about language models, open source, and sharing what I learn. And I work on the A-Stack open source LLM orchestration framework. But today, we are not talking about agents or RAG. We are talking about post-training, fine-tuning. But why fine-tuning language models? There may be a lot of good reasons for companies, including privacy, avoiding vendor lock-in, costs. But for a practitioner like me, this is useful to understand better how these models work, and it comes with some frustrations, but also a lot of fun. So let's dive into the topic. This is the agenda of the talk, and you can find all materials linked on GitHub, and you can scan this QR code. I'll show this also at the end of the talk. So we can start. A generative language model is simply a model that, given some text called prompt, generates other text. And the most common language models nowadays belong to the family of transformers. But how is it trained? This was a popular image on social that gives some understanding. So there's pre-training, then a part of supervised fine-tuning, and preference alignment. But let's take it a bit more seriously using this image by Maxime Labonne. So the first part is pre-training, where the model is shown a lot of text, trillion of tokens, and it is very costly. Generally, you cannot do this easily at home. And once the pre-training is finished, you get a base model which can just complete text. It's powerful, but if, for example, your prompt is how to make pizza, this can give you the recipe for pizza, which is what you want, probably. But it can also complete the sentence, how to make pizza, how to make pasta, or how to make pizza for a family of 6. So it's not usable right out of the box. And you need 2 other steps, and this is called fine-tuning or post-training. So the second and the third step, you can do this at home. And one step is to teach the model to follow instructions, and it's called supervised fine-tuning or instruction fine-tuning. While the third step is to align the model with human preferences. So in this case, you usually show a prompt, a good response, and a bad response. And in the end, you get a chat model you can use. But you can also reiterate these 2 steps at home to modify a model. So when do you need fine-tuning? The best thing to do is starting with prompting and prompt engineering and try to achieve your task with prompting. You can do vibe checking, but if you want to be more serious, you have to build an evaluation set and evaluate your model for your task on this. If the model gets good results, you're done. Otherwise, you can start fine-tuning and redo evaluation over time. And for evaluation, if you want to evaluate your model on common tasks, there are leaderboards, and there is also this library by Eleuter AI called LM Evaluation Harness. But if otherwise your task is particular, you have to build your own benchmark, and there is this recent project by Hugging Face called Your Bench, which makes it easier to build this domain-specific benchmark for you. So, yeah, you can explore your bench. Another important step is to choose the model to train. So you maybe want to use the base model coming from training or the already fine-tuned model. So what's the difference? If you start from the base model, you need more data, and you also need to teach your model to follow instructions. If you have fewer data, probably it's a good idea to start from an already instruct chat model you can find on the Hugging Face hub. And another tip from practice is to check on the Hugging Face hub if this model is popular in fine-tuning. There are many fine-tunes of it, because there may be very good models on benchmarks that for many different technical reasons, they are hard to further post-train or fine-tuning. There are a lot of training libraries. Here, there are just few of them. This talk will focus on TRL, Transformers Reinforcement Learning, from Hugging Face, which is great if you are already familiar with the Hugging Face ecosystem. Then Axolotl is also based on TRL, but is mostly about passing YAML configuration and train your model. Aslot is another popular choice if you have not much GPU, because it saves a lot of GPU, but also has some bugs I will talk about later. And then Llama Factory is a Chinese project which provides you with a graphical user interface. And so it's almost a no-code way of fine-tuning the model. And lately, also Verl became popular, and this is more about reinforcement learning. So if you need to fine-tune your model with GRPO, and it's maintained by ByteDance, the company behind TikTok. Let's dive into the most common post-training steps. We start with supervised fine-tuning. This is the kind of data you need, so a prompt or instruction, and a response. And with a good number of examples, your model can learn and generalize from this. And let's take a look at how to do this with TRL. You first have to load your dataset, in this case, an Italian dataset. Then you create a supervised fine-tuning configuration, including hyperparameters like learning rate and batch size. And then you create the trainer with the model name, the arguments, and the training dataset. And then you're ready to train. If you want to understand better how to do this in practice, I recommend two projects. One is from Maxime Labon. The other one on the right is a project of mine, where I improved the performance of Phi 3.5 Mini on Italian. And so, yeah, these are practical tutorials. You can also find them in the associated GitHub repository. Let's now talk about preference alignment. It first appeared in the Instruct GPT models and paper from OpenAI. The first step, we already covered it, is about training a model with supervised fine-tuning. Then what they did in preference alignment, they did reinforcement learning with human feedback with proximal policy optimization. So they took the model from the supervised fine-tuning step. They sampled it to produce several different responses, and then a human evaluator ranked these responses from best to worst, and then this data was used to train a reward model that then can be a proxy for human preferences. And in the third step, the model coming from supervised fine-tuning generates an output, and this output is evaluated using the reward model, and then using reinforcement learning, the model coming from supervised fine-tuning is trained. As you can see, there are several models involved. The necessity of a human evaluator, and so you use a lot of GPU resources, and this process is also unstable. So it gives good results, but in practice, it's hard to do this at home. So a simpler technique was invented called direct preference optimization. In this case, the problem is simplified. So you have preference data with a good response and a bad response, and this is transformed into a classification problem, and so you get rid of the reward model. You save memory, it's simpler, it leaves some performance on the table compared to PPO, but it's easy to use, and even Meta for Llama 3 used this technique. But let's see this in practice. So the data you need is a prompt, a chosen response, and a rejected response. In this case, both the responses are not bad, but the chosen response is more fluent. And when you have such data, you can use TRL, and also in this case, you load your dataset, you provide the DPO configuration, and then you initialize your trainer, and you can then train. I also recommend some tutorials about DPO. The one on the left is for DPO only by Maxime Labonne. And on the right, there is a project of mine called Gemma Neogenesis, where I improved Gemma on the Italian language using supervised fine-tuning and direct preference optimization. Fun fact, I took part to a Kaggle challenge, and I also won this challenge, but yeah, I think this is a good tutorial. I want to share some tips from practice. So, yeah, you need data, but producing data manually is costly. So you often use synthetic data produced from other language models. And this can work well. And yeah, this morning David gave a great talk on synthetic data. If you want to learn something about this big topic, I recommend Distillable, which is unfortunately an unmaintained framework, but comes with a lot of docs, tutorial, implementation of papers, and you can learn much about how to create this synthetic data. Then, yeah, also data preparation is important, and I share some useful links in the GitHub repo. Then, yeah, a silly thing that happened to me several times is no space left on device. You rent a GPU, and then at some point during training, the training stops, everything fails, just because, yeah, you don't have space on your disk for storing another copy of your model. So, yeah, when you choose your GPU instance, yeah, this is something to take into consideration. And about where to find GPU, I recommend Prime Intellect, which is a marketplace, and so you can access GPU from several providers, you can see prices, and you can spin up easily these instances yeah, through a unified interface. But speaking of GPU, I trained almost all my models using 48 GB VRAM for GPU on an instance which costs around 40 cents of dollar per hour. But to do this, you have to find strategies to do memory efficient training. So let's give a look at those. You may know LoRa, low-rank adapters. Here the idea is that during training, during backpropagation, if your model is a 7 billion parameters model, the matrix of weight updates is also contains 7 billion parameters. And yeah, this consumes GPU. And the authors of LoRa, based on previous literature, they think that this matrix of weight updates is rank deficient. And so they think, but yeah, in any case, they think that this rank deficient matrix can be approximated well with two low rank adapters. And in this case, the rank of, yeah, I was saying that we have these two low rank adapters. And so, in this case, the rank of these adapters is an hyperparameter you choose, and it has direct impact on the memory you use, but also on the fraction of the model you are updating. At the end of the training, these trained adapters are merged with the original model. And yeah, this saves GPU, but there is also an evolution of LoRa, which is very popular, and is called QLoRa. The main idea here is not to use the base model in precision, where each parameter uses 16 bits, but to use a quantized version of the model, a 4-bit quantized version, and they also use other GPU tricks, and in their paper, they managed to shrink the memory usage for fine-tuning Llama a lot. And this is very used in practice by people doing this at home. And if you want to do this with TRL, you first have to create a quantization configuration, to load your model using this quantization configuration, and then to provide a LoRa config where R, in this case 64, is the rank of this low ranker parameter, so the most important hyperparameter to choose. And then you can train. But I also want to introduce a Spectrum, which is less popular, but a good method. Here, the idea is to select beforehand which parts of the model you want to train. And so the authors try to discover which parts of the model are more important. And so the part of the model which have highest signal-to-noise ratio using matrix analysis. So once you have identified the most important parts of your model, you freeze all your model except for the parameters identified by Spectrum. And so here the idea is to save memory by selecting only a fraction of the model to be trained. And compared to Cullora, it achieves better performance in terms of performance comparison on several benchmarks, so it's competitive with full fine-tuning. But looking at memory efficiency, with Cullora on a single GPU, you can use less GPU, while Spectrum excels in distributed training with more GPUs. Let's see an example with TRL. So you first have to launch the Spectrum script to identify the parameters you want to train. And then you can load your model and freeze all the model except for those parameters identified by Spectrum. And then you can train. I also want to share some practical resources, both about Cullora and about Spectrum. You can find these resources on GitHub. Now, a totally different technique, model merging. And let's try to give a simple intuition. You have a model which is good at math and another one which is good at chatting. And the idea is to simply try, with several different techniques, to interpolate their weights in order to get one single merged model. And surprisingly, this works well, and you don't even need GPU. You only need much RAM, but CPU is sufficient. There are several techniques to do so, and a common library for model merging is called MergeKit. And as you can see, the configuration is pretty simple. You have to define the models you want to merge, the merge method, and some parameters that control the interpolation. And then you can launch this script, wait some minutes, and get your final model. And a very good article and practical example about model merging is this article. When I submitted this talk, the world was different because it was December. But in the last months, we have seen a lot of noise, but also a lot of interesting stuff about reasoning models and GRPO. So I also experimented with this, and I want to give you some ideas. First of all, what do we mean by reasoning model? It's just a language model that, before giving you the answer, produces a chain of thoughts. And so the final answer is based on this chain of thoughts. And this, especially for verifiable domains, can work better. But why do we need these reasoning models? So last year, at some point, we started hearing that that pre-training had diminishing retards. So we were throwing more money, more compute, more data into the pre-training phase, but the model showed little improvements. Then in December, OpenAI O1 model was released with a technical report, very short technical report, including this image. And this image shows that on a set of challenging math problems, you can improve performance, both increasing the train time compute and or the test time compute. So what this means? Let's talk for a moment about test time compute. The idea is that at inference time, with different techniques, you can have your model produce a number of responses. So you are sampling your model, and then you can use different techniques, tree-based techniques, Monte Carlo-based techniques, to select which is the best among all these answers. So you are investing more time and more compute in the inference phase. But about train time compute, what does this mean? Yeah, the O1 report didn't give details about this. But then, at some point, DeepSeek R1 was released, and they also described how they put smartly more compute into training. And so, let's talk about GRPO, which is Group Relative Policy Optimization, the technique used by DeepSeek. And here, we are also talking about reinforcement learning with verifiable rewards, meaning that it is applicable to verifiable domains like math. So how this GRPO works? We make the model generate a group of responses via sampling. Then each response is evaluated using deterministic reward function, not a model, just very simple function, as we will see. And we compute an average score across the group, and the individual responses are compared against this average. And so you can finally update your model using reinforcement learning to favor higher scoring responses. For language models, when we talk about reinforcement learning, there is always also a term called KL divergence that makes it sure that the new model does not diverge too much from the original model. So it's not pure reinforcement learning. Here, this is an image by Sebastian Raschka, which shows the models used with different techniques. As you can see in reinforcement learning with human feedback, with proximal policy optimization, 4 models were used. When you use GRPO, only 3 of them are used. But if your domain is verifiable, like math, and you can use deterministic reward function, you can totally get rid of the reward model. So you end up with just 2 models, and this is simpler, more efficient, and this is one of the reasons why this works, why this can scale, and also practitioners can use this. Let's take a look at data, which is very simple in this case. I'm using a sample from GSM-8K, which is a math dataset. So we have a question, a mathematical question, and this is visible to the model. Then we have the answer, very short, which is not visible to the model, but it is used for reward computation. As you can see, the data is pretty simple compared to supervised fine-tuning. So producing data for GRPO yeah, can cost not much. But yeah, to complement this data, you need the right reward function. So let's take a look at them. In this case, the first one is a correctness reward function. So here we compare the answer with, the right answer with the answer given by the model. And this function returns 2 if the answer is correct and 0 otherwise. Pretty simple. Then we have a format reward function, because when we train models to reason, we usually want them to put their chain of thought inside, for example, reasoning or think XML tags, and the final answer into answer XML tags. So this function gives 0.5 if the format is respected and 0 otherwise. And once we have data and we have these reward functions, we can use this with TRL, and we load the dataset. Yeah, we use the function defined earlier, and we create a configuration. And here, an important parameter is the number of generations, which is the size of the group. Usually, in practice, you use values starting from 8, and yeah, it's important to have a certain number, not too small, because you are increasing the diversity of your group, and you hope that at least one of these answers goes in the right direction. Then you define the GRPO trainer using the model name, you pass the reward functions, you pass the configuration and the training dataset, and then you can train. And about GRPO, I recommend 2 projects. One is a simple GitHub gist by William Brown. In this case, he trains the Llama 1 billion parameters model on GSM 8K. And then I also experimented a lot with GRPO, and I created this Quen scheduler GRPO. This is a specific problem in which I pass to the model a list of events with start times and end times, and a list of priorities. And I want the model to provide me with a schedule optimizing the time spent. And yeah, starting with a new problem forced me to set up this problem, to design reward functions, and then training by model, and seeing, after several iterations, that it improved. But yeah, I also learned several stuff I want to share with you about GRPO. As I said, GRPO works well for verifiable tasks like math, even if there are new papers that try to make it work for non-verifiable tasks. Then a comment about elicitation. From my experience and also papers, when you use GRPO and other reinforcement learning techniques applied to LLMs, you are eliciting some desirable behaviors from your models, but you are not teaching new stuff to the model. If you want to teach something new to your model, probably supervised fine-tuning, maybe with distillation from a bigger model, works better. And for this reason, the base model you choose to train matters. If trying to prompt your base model, you never see a promising direction. So your model never produces something that is similar to a good reasoning. Probably GRPO won't give you good results. So in this case, it's better to choose a better or bigger model. Another thing I learned is that in this case, designing reward functions is very important, and your reward functions should not be too steep. they should not penalize too much wrong behaviors from the model. Otherwise, your model cannot get signal to learn. So they should encourage your model to learn, even if there are errors. But at the same time, they should also be robust. Otherwise, you can experiment reward hacking. For example, in my experiment, at some point, I saw that the results were increasing, the numbers were getting good. Then I expected the text that my model was producing, and my model discovered a problem in my reward function. So they were just producing schedules with just a single event, and yeah, just a single event. And in this case, the model chose a priority event. So yeah, the schedule was in chronological order. There were no overlapping events. But yeah, this was not the problem I had in mind. So if your reward functions are not robust, the model will find a shortcut. Yeah, a quick thought about the aha moment from the DeepSeek R1 technical report. They said that using GRPO, the model developed anthropic self-thinking capabilities. And yeah, this was impressive. But then recent studies shows that also the base model they used had these behaviors, and probably GRPO only favored this behavior. So yeah, in this case, GRPO probably don't create emergent capabilities, but just favors behavior that we want. Yeah, and I thought about Unslot, which is great if you want to experiment, if you are on Kaggle or on Colab, but it patches a lot of other libraries underneath. And in the end, with Unslot, I wasn't able to convert the model trained with Unslot to a common PyTorch or transformer model due to a bug. So yeah, if you have to experiment and yeah, you have a free GPU on Kaggle on Colab, use it. But if you are doing something serious, yeah, probably using TRL is more stable. But yeah, now let's go to the part you maybe were waiting for. So how to run these small language models on a phone. So these models locally in the phone. The response is simple. You first need to convert your PyTorch or Transformers model into GGUF. GGUF is a format from Georgy Georganov, the creator of Llama CPP. And when you have a model with GGUF format, it runs on CPU only. If you have GPU, this is better, but it can only run on CPU. And there are two ways to do this. You can use this Hugging Face space. You put your model there and you wait. Or you can go to the programmatic way using this Llama CPP script. And once you have a GGUF model, and you can find many of them on the Hugging Face hub, there are people constantly creating quantized version of models. You need an app. Yeah, this Pocket Pal AI app is very simple to use. And yeah, you can then download your model on your phone. Here, yeah, you can see myself with this phone from 2022. Not a cheap phone. And here I registered a video of me trying to run this model on my phone. I'm asking the model to say hello to the people of PyCon Italy. This is a model I personally fine-tuned starting from Gemma. This takes some time. But yeah, as you can see, it starts responding. And yeah, it's probably not so bad. It's also excited to be part of PyCon Italy. So great. I also want to see if it can, produce some text in Italian. Yeah, you still have to wait some more moments. And yeah, probably the response is, yeah, not bad, but also not great. And he's saying, ciao a tutti, sono un piccolo modello linguistico attualmente ospitato su questo semplice smartphone. And is enthusiast to be part of PyCon Italy. Yeah. And yeah, nothing fancy, but it's fun to have your model on your phone, without data leaving your phone. And yeah, with that said, thank you. And here you can find all materials, all my social profiles, everything, and I wait your questions, if any.
Thank you for the talk. You have a lot of questions. Let's load it. Okay. Okay. There are a couple about how many samples do you use or do you need to tune an LLM, and it depends on the model, but
yeah. Yeah, it depends on your task, but if you start from an already fine-tuned model, you maybe use Coolora, generally to start seeing with supervised fine-tuning, to start seeing changes of behaviors on your model. You can, you sometimes start seeing this changing with 100 samples, but if you have more, is better. If your task is more difficult, for example, in my case, I tried to improve it on the Italian language, and so in this case, having like tens of thousands of examples is better, but you can start with hundreds.
Okay. And a question about model merging. During model merging, we need to have the same model architecture and parameter numbers so we can create a Frankenstein and a Frankenstein with a...
Yeah, there are a lot of experiments. For what I know, the experiments that work better, you use model with the same architecture. But there are also experiments, there is Franken merging, and so, there are also strange parameters named in this library called, for example, hello crimes. So you can experiment a lot. For example, some time ago, starting from Llama 3, 70 billions, someone also tried to self-merge the model, producing Llama 105 billions, and it was good for creative writing, so you can do a lot of experiments. Yeah, the best experiments, usually they come from using the same architecture, but it's not mandatory. And there is also another part I haven't talked about, which is obliteration. So how to remove guardrails from your model. And this is in some way related to model merging, because you are modifying the weights without actually fine-tuning, but acting as a surgeon on the weights. And very interesting, I would say.
Okay, so it could be strange sometimes, but... Okay, it is possible to reward symbolic reasoning to solve math problems instead of numeric results. Are shortcomings to this approach? This is a complex one.
I have seen some papers, research on this topic, but I don't know if there are open source reproducible ways to combine symbolic reasoning with language models. I've heard of some papers, and some closed source ways, but yeah, I don't have experience of seeing the actual code to do this. So yeah, it's interesting, but I don't have much information about.
Okay, last question. When using GRPO, how sparse can the reward function be?
Sorry?
How sparse the reward function can be? And I don't know who did it. Okay.
I haven't understood this well, but in my case, for example, of this, in my case of the scheduling problem, I tried several combinations of reward function. For example, at the beginning, I was using a very simple reward function that was one for format, which is simple. The other one, the goal was to score the schedule, and if the schedule was right, give I don't know 1, otherwise 0. So this took everything into consideration: overlapping events, number of events, chronological order, and this didn't work. Because most of the times, especially at the beginning of the training, my model got 0, and so this function was not providing a signal for the model to learn. And in the end, I used 3 or 4 different reward functions that get summed, and this worked better. But I don't know if the question about sparsity was about these details or something else.
Okay, let's thank Stefano, and if someone wants to know more information about his answer, he can talk with him during the coffee break, okay? Thank you.